Hey everybody, welcome back. This is CHEM300 and today we are continuing chapter 8. So we're going to be talking about theoretical yield and percent yield in this section. So our goals are to define theoretical yield, actual yield, and percent yield, then learn how to calculate the theoretical yield for a chemical reaction, and then how to calculate the percent yield for a chemical reaction. We're going to be doing some word problems in this section as well as in the following section, which is where I'll work through several additional example problems related to stoichiometry. So let's start with some definitions. Let's start with theoretical yield. The theoretical yield is the maximum amount of product that can be made from given amounts of reactants for a reaction if no losses or inefficiencies of any kind occur. So this is the maximum amount of product you can make when you use up all of the limiting reactant in a chemical reaction. And it's assuming that you don't have any mistakes in the reaction, that you make 100% of the product that could possibly be made, which we know based on limiting reactants, once the limiting reactant runs out, you don't make any more product. So how we figure out the theoretical yield is we calculate how much product is made by the limiting reactant. And so we've actually already been calculating theoretical yield in the limiting reactant section. We just didn't call it the theoretical yield yet, but it's the maximum amount of product that's made by the limiting reactant. It's different from actual yield because actual yield is what you actually weigh or measure in the lab when you do a reaction. So theoretical yield is based on a balanced chemical equation and stoichiometry and how much reactant you start with. So you're calculating if all the reactant is 100% converted and you don't make any mistakes in the lab, what's the most product you can make? Actual yield is what you actually get in the lab. So it's like once you've done your chemical reaction, you collect your product, and then you go and you weigh it or you analyze it to figure out how much you actually got. So it's really common for the actual yield to be less than the theoretical yield. Something will sometimes just happen in the lab, like you drop a little bit of one of your reactants, you don't weigh things quite as accurately as you needed to. Maybe you had to filter your product to collect it at the end and you lost some of the product in the filtration step. There's lots of ways that your actual yield could be less than the theoretical yield, like you didn't collect as much product as you could at the maximum amount possible. So the percent yield gives you an indication of how well you did. Kind of like when you calculate your percent on an exam, you look at how many points you got divided by how many points are possible. It's the same thing for percent yield in the chemistry reaction. We take the actual yield, how much you actually got, divided by the theoretical yield, the total amount possible. So it's just like calculating your percent on an exam. You take how many points you got, divided by how many points were possible, and multiply that by 100 to find your percent. In a chemical reaction, you take how much product you actually got, divided by the total amount of product you could have gotten if you had a perfect chemical reaction, multiply it by 100 to change it into a percent, and that's your percent yield. So again, it's very common to get percent yields that are less than 100%. All that means is that your actual yield was less than your theoretical yield. Like you lost some of your product during the chemical reaction, or maybe you didn't transfer all of your reactants that you weighed out into the reaction vessel to do the reaction. That would also cause a low percent yield. Occasionally, you'll get a percent yield that's over 100%. This is impossible in the real world. You can't make more product than we theoretically calculated you can make. But what will sometimes happen is that if your product gets contaminated or weighs more than it should at the end of the reaction, that will cause your percent yield to be over 100% because your actual yield will be more than the theoretical yield. What commonly causes this is that if you have a product that you have to filter that's like a precipitate in solution, you've got to filter the precipitate to separate it out of the rest of the solution. If that precipitate isn't all the way dry when you go to weigh it, it's going to be heavier than it should be because it still has water around it. So that's a really common way that you might accidentally get a percent yield that's over 100% if your product sample isn't all the way dry and it needs to be all the way dry to weigh it. So let's do a couple of examples with percent yield. So what would be the percent yield of a product for a chemical reaction where the theoretical yield is 5.6 grams and the actual yield is 4.5 grams? So in this problem, we're given the theoretical yield. We already did some stoichiometry to calculate how much product we could make if all the limiting reactant was used up. And then what we actually got in the lab was 4.5 grams. So to figure out the percent yield, you take your actual yield, 4.5 grams, divided by your theoretical yield, the most you could have gotten, and then multiply that by 100. Let's see what we get. 4.5 divided by 5.6 times 100, and I got 80.80%. with 2 sig figs because we had 2 sig figs in each of our masses. So the answer should be B, 80% with 2 sig figs. So that's how you calculate percent yield if you have the actual yield and the theoretical yield. The actual yield is something you have to measure. So typically it's given in a problem. If you are not given the actual yield, it means that you know the percent yield already and you know the theoretical yield. So you could rearrange this equation to solve for actual yield. Another way you might use this equation is if you're given the percent yield and you're given the actual yield, you could calculate the theoretical yield by rearranging this equation. Okay, let's do another example problem. So nitrogen gas and hydrogen gas react together to form ammonia. Given 75 grams of nitrogen and 45 grams of hydrogen, how many grams of ammonia can be made? And then if 86 grams of ammonia is actually produced in the reaction, what is the percent yield? So let's do this one on a whiteboard so we have a little bit more space to work it out. So first thing we have to do in order to do any sort of stoichiometric problem, chemical calculation problem, is we have to write and balance the chemical equation. So we have nitrogen gas reacts with hydrogen gas to make ammonia gas. And we need to balance it so that when we do stoichiometry, we have the correct coefficients or molar ratios in our balanced chemical equation. So we're going to need a 2 here in front of ammonia, which gives us a 3 in front of hydrogen. And now everything's balanced. So we're given the actual yield, 86 grams of ammonia is actually produced, and we need to calculate the percent yield. So percent yield is actual over theoretical times 100. We're given the actual, so we need to calculate the theoretical yield. And the theoretical yield is the max amount of product produced by the limiting reactant. So to figure out our theoretical yield so we can plug it into our equation for percent yield, we have to figure out which one of our reactants is the limiting reactant and then how much product that limiting reactant makes. That gives us the theoretical yield. So that's what it's asking us to do in part A. It gives us the amounts of each reactant, 75 grams of nitrogen, 45 grams of hydrogen, wants us to figure out how many grams of ammonia can be made. So to figure this out, we've got to take each of those reactants, 75 grams of nitrogen, and figure out how much product that's going to make. 1 mole of nitrogen weighs 28.02 grams. And then we use our chemical equation. For every 1 mole of nitrogen that reacts, we make 2 moles of ammonia. And then 1 mole of ammonia, using its molar mass, weighs 17.04 grams. And that'll give us our mass of ammonia made if we react all of the nitrogen. We've got to do the same thing with our hydrogen, and whichever reactant makes the least amount of product, that's our limiting reactant, and the amount of product that it makes is the theoretical yield. So let's figure out our amount of product made from nitrogen. 75 grams times 2 times 17.04 divided by 28.02. So I get 91.22 grams of ammonia made if we react all the nitrogen. Let's do the same thing with hydrogen. We have 45 grams of hydrogen. We need to convert that to moles because you can't do stoichiometry without going through moles. The molar mass of hydrogen is 2.02 grams per mole. Now we're going to use the coefficient. So 3 moles of hydrogen react to make 2 moles of ammonia. And 1 mole of ammonia weighs 17.04 grams. So let's see how much ammonia we would make if we reacted all of the hydrogen. And I get 253 3.06 grams of ammonia. And that would have 3 sig figs if we were done with our problem. Okay, so now we know which our limiting reactant is. N2 is our limiting reactant because it made the least amount of ammonia, made 91.2 grams versus if we reacted all the hydrogen and make 253 grams. So this is our theoretical yield. It's the amount of product made when all the limiting reactant is used up. Because once all the limiting reactant, the nitrogen in this case, is used up, the whole reaction stops, so we can't make any more product. So we figure out which ones are limiting reactant and the amount of product that it makes, that's our theoretical yield. So now to calculate the percent yield, it's our actual divided by our theoretical times 100. So we were given that we've actually produced 86 grams of ammonia. That's how much we weighed out after we did this reaction. And we theoretically, if we did a perfect reaction, didn't have any losses, could have produced 91.2 grams of ammonia. So we're going to divide those two and then multiply by 100 to give us our percent yield. So 86 divided by 91.2 times 100 gives us 94.29. If we round that to 2 sig figs, because we've got 2 sig figs and 86 grams, our actual yield gives us 94% yield. Which is excellent. 94% yield anywhere in the 90s is typically pretty good for a chemical reaction, because we know that just stuff happens in the lab. Maybe you don't perfectly transfer all of your nitrogen or hydrogen into the reaction vessel to start the reaction. So if you start out with a little bit less reactant than you calculated, it's going to make your product amount that you generate go down. Or if we had to somehow filter or separate the product to weigh it, there can be losses there as well. So we end up with a 94% yield. And to get here, we had to write and balance the chemical equation. We had to figure out, based on our starting amounts of each of our reactants, which one was the limiting reactant. And then the amount of product that the limiting reactant makes, that's the theoretical yield. That's the maximum amount of product that could possibly be made. And then we used our given actual yield and our calculated theoretical yield to calculate the percent yield of 94%. Okay, so that's it for this section on limiting theoretical yield and percent yield. We're next going to do a whole bunch of examples about stoichiometry. We're going to start with one about carbon dioxide and global warming, and then do some other kind of more challenging stoichiometric problems as part of these examples. At the end of the next section, I have links to some videos, YouTube videos that I found really helpful on how to do stoichiometry. So be sure to check those out at the end of the next section if you want additional help with stoichiometry. I'll see you then. Thanks, everybody.